Okay, welcome everyone back. So we will continue with session 2, and I would like to introduce Professor François Joint from Chalmers, and he has a talk entitled "The RF Engineering Behind Radio Telescopes." So welcome, Professor Joint. So you have the floor now, please.
Thank you, Esteban, and thank you everyone for coming to the talk. And I will try to share my screen up. So, Esteban, can you confirm you see the slide?
Yes.
It changed. Oh, wait, give me a second. It changed, right?
Yes.
Okay. So let me
now
put
it's
it.
back.
Yeah, let me put the. Yes, thank you, Esteban, and thank you, everyone. So I'm François, and I will talk about the RF engineering behind radio telescope. I'm from the Onsala Space Observatory at Chalmers University of Technology in Sweden. So let's start with something familiar to everyone. So that's this is the night sky you can see with your naked eyes in your backyard in the wintertime from the northern hemisphere. And this is the Orion constellation that you can see. You can find Betelgeuse, one of the bright star in the night sky in winter, and Rigel, and Orion's belt, if you're familiar with your constellation. And if you're lucky with a low night pollution, you might be able to see some a very faint color, white color around the belt. And what misses in this picture is actually the cold gas and dust that you would see if you were using a radio telescope. So actually I would zoom in, so around this region, and I would use a powerful radio telescope and terahertz sensors to see how it looks like. And if you are using Spitzer, this instrument, you'll be able to record basically the gas and the molecular clouds and dust of the Orion's belt, or of the Orion clouds. And so in this image, we have a superposition of a spectra and Spitzer image that recorded the light intensity. And here we color them in green and red, depending on the wavelengths. And below, as you see, I mentioned, there's a spectra, and that's what would interest us in this talk. You see the spectra contain a lot of lines. It was taken with the instrument I-5 from the Herschel Space Telescope. And each spikes in this spectra represent a molecular transition. And if you see in the labels, you can recognize some famous molecules such as water, carbon monoxide, methanol, and with the spectra, astronomers have been able to identify the composition of this molecular cloud in the interstellar medium. This is the place where planets and stars are forming in the space. So a little bit of orientation so you can read a spectra. So on the x-axis, usually we plot the frequencies, or in astronomy, we also plot the velocity because we know the Doppler shifts tell us the motion along the line of sight. On the y-axis, we plot the intensity. It's a brightness temperature in Kelvin usually, or flux density in Jansky. And the area below the lines, usually it's an integrated intensity, and it relates how much of the specific molecules is along the line of sight. So with just these two axes, we can now read a bit the spectrum that we get in radio astronomy. And before I move on into hardware, I want to give you some explanation how to read in more detail the spectral line. So a spectral line in the spectrum, as we've seen in the spectra before, contains many information. And the most important information is I would say the F0, the rest frequency, which identify the species and the transition of the molecular line. So with a logbook of molecule spectral line that has been identified in laboratories, we can identify molecule in space using this catalog of F0. The second most important feature in this spectra is the line stress, the intensity, and this basically tells you about the column density and excitation, how much and how warm do we have of this molecule. And the third important features in the spectra is the width of the molecular line, and that tells us about the turbulences of the molecular clouds, of this how fast the cloud is collapsing together within itself, how the wind inside this cloud. It tells you also the temperature of the cloud. So the hotter the cloud is, the broader the transition will be. Of course, the last important features is this shift, so delta F, which compared to the rest frequency, it tells you about it's the redshift. It will tell you the Doppler shift. It will tell you the radial velocity of the clouds. And that's about it for understanding basically a spectrum from radio astronomy. So to get this kind of spectrum, astronomers use a heterodyne receiver. So a heterodyne receiver provides the highest spectral resolution in the instrumentation, so in the 10 to the 6 to 10 to the 7. Usually we use velocity, as I mentioned, so it's just a conversion of the spectral resolution into velocity in kilometers per second. And the basic idea, it generates a signal of the same shape into a frequency range that we can work with. So it's called a coherent receiver, and we basically mix the observed signal, I would call it the sky frequency, with a pure local oscillator. I will define that later. And through this heterodyne receiver, it will shift down the sky frequency to an intermediate frequency, you see at lower frequency, where we can amplify and analyze this extremely fine spectral tones. So it's basically using a radio in a car, but in the millimeter wave and in the terahertz. So the importance of heterodyning is down converting and without losing any information. So there is two types of detectors that I showed you earlier. So in this IFI and Spitzer overlay image, we first have the direct detections. So most commonly the bolometers, they are incoherent. Among them, we find the kinetic inductance detectors and the bolometers. They are superconducting devices, very extremely sensitive, and they are quite good for wide field imaging. That's why we could see with Spitzer the full image of the clouds. And it's also used for polarimetry measurements. The only thing with this detector, the incoherent detector, we don't get the phase information of the signal. We just see the intensity. That's why in radio astronomy, we use coherent detection, so heterodyning. And this time we use instruments such as SIS or HEB mixers. And those mixers actually conserve the amplitude and the phase of the incoming signal. So that's what allows us to get a very high resolution spectroscopy and interferometry. So in this talk, I will focus mostly on coherent detection, the heterodyne receivers, because that's what interests us for looking at this complex spectra in stellar medium. So while the incoherent detectors have basically only the background limit, so now we have detectors that can be that has better sensitivity than the photon shot noise. In coherent detection, we have a limit, the quantum noise limit, and it's really determined by h nu over 2 kb. So that's the fundamental limit that we can't break in coherent detection. So now if I go back into what is the functioning of heterodyne? So when you mix RF spectrum, so the sky signal that you're looking at with a local oscillator signal, the signal above and below the local oscillator will be down converted to the intermediate frequency range. In a DSB, we have two types of heterodyne mixers. The most common and the most simple is a double sideband heterodyne mixer. So in this scheme, in the DSB scheme, the upper and lower sideband will be overlaid around the intermediate frequency signal. And the advantage is that we get twice as much of continuum power. And the device is quite simple. We just need a mixer, local oscillator, and an NIF chain. The only thing is that the DSB lead to confusion of lines. So you see that in this configuration, I will confuse lines that were contained in LSB in the lower sideband and the upper sideband. That's why most of the modern observatory nowadays use single sideband or double sideband heterodyne system. In this system, we can separate and split upper and lower sideband. So the payoff is we have cleaner baseline. We don't have any spectral line confusion or less. And of course, it divides the observation time by 2 before we can reach the spectral goal. The only thing is a bit more complex instrumentation, and you will see that a bit later in the talk, since we need more hardware in order to split upper and lower sideband. So in a nutshell, the heterodyne receiver start. I will follow the signal and build the heterodyne receiver. So we start from I would call it the RF signal or the sky signal, the signal of interest from the astronomical object, the clouds, interstellar medium, which has a very high frequency. I have a local oscillator. It's a pure tone generated in the telescope with a very good reference. We have the mixer. It's a very highly nonlinear system that can mix the RF and the LO together to generate, and we have a duplexer. So the RF signal and the local oscillator signal are overlaid together using a duplexer. So usually it's a very thin film of mylar. It could be more complex setup like a Martin Puplet duplexer. There's plenty of ways to overlay these two signals. Once we have overlaid LO and RF signal, they are both impinging on the mixer, this nonlinear system, which will generate a down-converted signal at the intermediate frequency, where usually we can use preamplification. So HEMT, usually this high electron mobility transistors with high gain and low noise. And down the line, we use ADC, so a setup that can convert weak signal after the preamp into a digital signal that we can record and save and analyze further down the line. So that's the basic idea of an heterodyne receiver. This one, I don't precise the optics, but that's the most broad representation of the heterodyne scheme. So in this talk, that's why I wanted to call the RF engineering behind the radio telescope. We'll talk a lot about terrace electronics, so which includes for superconductivity knowledge using with SIS, HAB, or tracking mixers. We'll talk about sources, terrace sources, and we talk about Gaussian optics as well, HEMT amplifiers, noise. And actually, this talk is a condensate of a course we give at Chalmers on radio astronomy and technology, which normally is on 8 weeks, but today it will be 45 minutes. So hold on. And now that I introduced heterodyne receiver, I will focus a bit more on radio observatory, and I will follow some examples. Before I start with that, I want to look at the light spectrum and the corresponding atmosphere transmission. This will decide how we will do the observation. So you see that the gray areas in this plot is correspond to the water and oxygen absorption. So and the blue is basically where the sky opens. So you see that in the millimeter wave and the sub-millimeter wave, so in this terrace region, the sky is more or less opaque. And that's why we need to choose our site where to observe. So if you use Apex telescope or ALMA telescope in Chile, in a very high altitude where the sky is quite dry, low precipitation, in this range, you have openings where you can observe without having the penalty of this atmosphere transmission. In the terrace, at the sub-millimeter range, so shorter wavelengths, there's the sky is totally opaque. And in that case, we need to use stratospheric plane or balloon in order to do the observation, to remove this this opacity of the sky. And once you go in these altitudes, you start to see more lines, molecular lines in the space. And the top notch is actually space telescope, because then you don't have any atmosphere, and you have access to the full infrared and far infrared and terrestrial spectrums with an extremely stable background. And of course, an uninterrupted coverage. There's no winter, there's no summer, so no rain, no snow. The only high price of space observation is that it's extremely expensive. You have a limited aperture, so compared to a ground-based telescope where you can afford 12-meter dish, in space you can have maybe half a meter aperture. You are limited in size, of course, and of course in cost. So Herschel finished in 2013, and since we have no infrared space telescope, far infrared space telescope, and we hope to have more coming. And now we just limited with ground-based telescope like APEX, ALMA, STO, the stratospheric balloon, and Sophia also retired last year. So in a nutshell, the science goal will basically dictate the platform that we want to use for making this observation. Sometime also one precision, so lines that we have to observe in the far infrared with stratospheric balloon or space telescope can fall in the ground-based telescope sites with some help with the universe, with the redshift. So if some lines are redshifted by the distance from the observation points, they can fall in the ground-based telescope's observation capability. So I will focus today on ground-based telescope because it's what we do at Chalmers. Chalmers is involved Onsala Space Observatory is involved in 3 observatory, the APEX. So it's a 12-meter dish, single dish in the Atacama Desert at 5,000 meters altitude. It can perform fast line scanning. It has a wide IF range. It's a single pixel. It's also used for pathfinding, instrument pathfinding. So inside we have the instrument called Sepia, which is similar to ALMA instrumentation with similar bands. And Chalmers worked on band 5, band 7, and band 9. It used 2SB SAS mixers with wide IF. ALMA is in the concept similar to APEX, but it's an interferometer. It has 66 dishes on the square size baseline, 5,000 meters altitude, and it has a very high angular resolution in the millimeter wavelengths. So basically, ALMA turned this spectrum that I showed you earlier into maps of kinematics in the astronomical units range to parsec range. So I will show you some results with ALMA a bit later in the talk. So in OZO, we developed band 5 and band 2 of ALMA. And in Sweden, so at Onsala, close to Chalmers, we can't do the same observation as we would do in Chile, because in Sweden we have a very wet atmosphere. So, but we can observe up to 116 gigahertz using the 20 meters telescope inside this radome, and it's mostly used for spectral line astronomy. And also geodetic VLBI, and I won't touch about VLBI today, but it's another application of radio astronomy. So let's focus today on APEX. So APEX, as I said, it's a 12-meter dish at 5 kilometer altitude in the Atacama Desert. It's possible to observe in the millimeter wave because of this specifically dry atmosphere in Chile, in this desert. So you see that that's the model of the atmospheric transmission for different precipitation rates, and you see that the transmission is pretty good in the millimeter wave, and for band 5, band 7, and band 9, we have a lot of openings in the atmosphere where we can perform observation. So there's two rule of thumbs for development of radio telescope. So of course the size of the dish and the surface accuracy of the dish. So you see that to perform observation in the millimeter range, you need to have the dish with a surface accuracy below 15 micron RMS. We have that for the primary dish. We have a secondary dish with about 0.75 meter diameter. So that provides a very narrow pointing line of sight. So basically, this parameters limit will basically give you the upper limit of the frequency that you can use for this telescope. And you also define basically the optical path later on for the instrumentation and basically the limits of the spillover that you will have and the cross pole that you will get for this instrumentation. So there's different type of antenna. So I showed Apex. Apex is a Cassegrain with a Nasmyth cabin. So the role of antennas is threefold. As you can imagine, it's the main goal is to collect as much as possible power coming from the space. It's also its second role is to form a very clean beam on the sky, and of course deliver this beam to the receiver, to the instrumentation with minimal loss. So we have a few, I would say there is few arrangement for radio telescope. So Cassegrain Nasmyth, so where we have the primary, secondary mirror and a tertiary mirror that's allowed to send the beam into a cabin, a Nasmyth cabin, where we can and store the instrumentation. So this Nasmyth cabin is a stable room with a thermally controlled, thermally stable, and not without the noise of the telescope moving around. So that's Nasmyth cabin. At ALMA, it's an on-axis Cassegrain, if I remember well, telescope without the Nasmyth cabin. Well, we have also the Gregorian and prime focus options. So all those techniques give different trade-off in terms of blockage of the signal and spillover, and of course in the available instrumentation box weight you can use. That's for the role of the antenna. So now if I go inside the Nasmyth cabin, as I said, so once the light hits the primary, it would reflect on the secondary and then the tertiary mirror to shoot into the Nasmyth cabin. And we have a bit more optics inside to bring into the receiver into the receiver box. So a lot of the alignment is done on site and optimized on site. And so at Apex, there's optics that's allowed to select also different instrumentation. So in the sepia instrumentation, we have 3 different instruments for 3 different bands. So here's more pictures about the Nasmyth cabin. So you see the primary mirror, secondary, tertiary inside, and that is the Nasmyth cabin, where we have this cryostat. So all the instrumentation most of the sensors are cold, and so we need to use cryostat. And here again, has some optics in order to select between instrumentation. So the sepia, as I said, it's a single pixel heterodyne front end. Inside there's 3 cartridges. So I'll show what is the cartridges later. It has ALMA style cartridges, ALMA style receivers. So we have a band 5 receiver which covers 159 to 211 gigahertz. It's a 2SB mixer with an automode transducer in front. We have an ALMA band 7, the sepia 345, covering 272 to 376 gigahertz, 2SB, and a sepia 660 band 9 corresponding to ALMA, going up to 725 gigahertz in 2SB, installed in 2018. So the cartridges is like this. So you see that there's a bit more optics inside even to focus into the receiver. The cartridges is like a mini fridge, with different temperature plates. So we have a vacuum jacket to prevent that the atmosphere freeze on the cold plates. We have different stage of temperature, so the 110K plates. That's allowed to isolate the lowest temperature from the background at the outdoor temperature. We have here in this stage, we have some cold electronics, the amplifiers, the amps. I'll show them a bit later. And here we have the receiver itself. And I will go into much more detail later to show how it looks like inside. But that's basically the ALMA style cartridge that we use in radio astronomy instrumentation. So rather complex. So inside this cartridge, you would find a receiver like that. That's a typical 2SB receiver. We start with a corrugated horn. So at the entrance of the receiver, it's the final optical element that we have in the cartridge. It's that's allowed to couple from the telescope all the way down to the receiver. So we use a corrugated horn, feed horn, that helps to shape the beam and minimize the spillover. And just after the horn, we have an orthomode transducer. It's a acronym for OMT, and splits the incoming signal into two linear polarization, vertical and horizontal. And each polarization goes on a different path to different mixer. Here we have one 2SB mixers and a second 2SB mixers. So we double the efficiency and without compromising the sensitivity. And here we have more electronics, so the hybrids, isolators, and amps. And I will go through them one by one. So as I said, the OMT split into Y and X and Y pole, and all that sits at 4 Kelvin in the instrumentation cryostat. So an OMT is quite essential tools because, as I said, it's split into vertical and horizontal polarization. It's also a complex system to do in waveguide. You see that you come with the square aperture coming from the field horn, and you need to split into rectangular output without losing much of the signal. So that since that's what the signal sees first after the field horn. So in the waveguide blocks, it becomes a bit of a complex engineering to design and to simulate. So the sideband separation, so as I mentioned, it's extremely complex. It's a bit more complex than double sidebands because it involves many more instrument devices. At first, after the OMT, we have, for each side, we will find a 90 degrees RF hybrid, which split the signal in two paths, again, with equal amplitude and quadrature phase shift. So the two quadrature phase shift, the two quadrature are fed into two SAS mixers. And after the mixing, we have another hybrid. This one is the IF hybrid, 90 degree, that will recombine the two signal into two outputs to get upper sideband and the lower sideband. That's how we get sideband separation in a heterodyne receiver. So the sideband separation actually lives and die on how well the two paths are balanced. So that's what I'm showing here in this plot. Is most of the instrumentation for ALMA and APEX require a sideband rejection. So basically isolation between USB and LSB better than 20 dB or 15 dB, and that's required to have an amplitude imbalance better than 0.5 dB, 0.5 dB, and a phase better than 5 degrees. So that's the sweet spot where we live basically in sideband rejection. So as I said, the sideband rejection is very sensitive to small errors and can be optimized using local oscillator pumping, and I will show that later. But that's why 2SB is a I would say microwave RF engineering challenge for us as well. Now I've talked about front end and techniques for heterodyning, and now I want to focus a bit more in the role of receiver. So the heterodyne receiver has one mission, is to turn a faint astronomical faint signal into a stable and calibrated high-resolution spectrum. So we have to couple the beam cleanly from using feeds, OMTs, and Cole optics, don't convert the signal without adding any more noise, amplify this don't convert the signal with amplifiers, and quietly, and preserve basically the phase and amplitude of the initial signal. So so we'll talk about these front ends and how we calibrate them a bit later. So before I move forward, so we have this at ALMA, for example, I take an example of ALMA this time. We have about 10 different receivers covering 10 different frequency band. So depending of the frequency and the upgrade, so this actually might not be all the way up to date, but they have different hardwares. Some of them are single sideband. I mean that one sideband is terminated with a 50 ohm load. Some of them, like band 5, is 2SB. Band 9 is also 2SB now. Some of them don't have autonomous transistor. They would use wire grid polarization. So because depending on the bands, this is actually quite challenging to realize as well. So here is the latest updated pictures of what ALMA fridge looks like with the 10 cartridges inside. So we have one of such in every 66 dishes in ALMA. So it's a lot of hardware, and it's also why it costs $1 billion to build. So it's a lot of hardware, it's a lot of research development in microwave and optics, and a lot of tuning. So among receivers, there's an IF system. There's basically two canonical architectures, basically. So in the lower millimeter wave range, so I would say up to 100 gigahertz, so we can use an amplifier first at cryogenic. So we won't use a mixer first, we would use an amplifier, a HAM, so LNA, that will basically amplify it, and then we would use a mixer later on to down convert the signal while keeping the gain and linearity. So nowadays, those LNAs are extremely good in terms of noise temperature at this frequency. And if you go at frequencies above 100 gigahertz, then we will need to use a mixer. So SAS, I will show what is SAS later. So and we then use LNA after the first mixer. So I would say up to 1 terahertz we use SAS mixer here, and above 1 terahertz we use HEB, so hot electron bolometers. So this is basically the dividing line between available devices and noise, temperature, and waveguide losses that we have available before we amplify, between amplify first or mixing first. That's basically the two, I would say, the two architectures you would find in radio astronomy. So yeah, nowadays the core amplifiers, they need about 15K of temperature, and it's a two-stage cryostat. If you need SAS mixers, it's a bit more complex. You need to go at 4 Kelvin, and you'll see why later. And we need a bit more complex cryostat with a 2-3 stage. So back again to my 2SB receivers. So I showed earlier the feed horn, the OMT, and now I will focus on the 2SB mixer itself, the SAS. So at the heart of this receiver, we have the SAS mixer. It's a superconducting tuner junction, which works at 4 Kelvin. So it's quite closely related to the Nobel Prize in Physics of this year. So basically, this device helps to combine the sky frequency with the local oscillator. And the SAS basically is a high nonlinearity that's allowed to down convert into an IF. So in band 5 and band 7 in ALMA, we use a 2SB architecture to keep, of course, USB and LSB cleanly separated. And in band 9, we also use SAS, although it's closer to the gap frequency of the superconductor. So here, I would like you to appreciate the size of the devices. So that's a SAS mixer chip that make this down conversion. So in general, the device is about 2 millimeter long and 200 micron wide. So we used probe antennas to probe a waveguide where the signal comes from the antenna, and then the IF is extracted through wire bond and through PCB. So if I look from this images, so in the scale at 500 micron, actually the SIS itself is much smaller. It's about 1 micrometer in diameter. That is the SIS. That is this tunnel junction that make the whole magic happening. And if I zoom even further, if I take a cross section of this SIS, what it looks like, it's basically an insulator in between two superconducting material. So here's niobium and here's aluminium. And the thickness of this tunnel barrier is about 1.25 nanometers, so extremely small. So if I look at how it looks like in when I do a DC characterization of this SIS, so you recognize that for unpumped SIS, you have the superconducting gap. That means that there's no tunneling. Eventually, at the gap voltage, so for niobium, it's about 2.9 millivolts, we have tunneling, and then we have a normal transmission, a normal resistance. So in the SIS mixers, we use we do photon-assisted tunneling. That means that if we bring a local oscillator near on this SIS, we'll see steps appearing. So the famously known Shapiro steps appearing in this IV curve. And that's where we bias our device. Usually we pump the device with the local oscillator, so we see this Shapiro step appearing, and then we voltage bias the device. So we get the best sensitivity. So when a very faint signal coming from the sky comes in, it's just enough energy to have the quasi-particle to tunnel through the barrier. And that's what the mixing is about. It's all about fine-tuning the mixer into this more sensitivity states with the local oscillator and the biasing, and extracting this mixing signal with the IF circuitry. So maybe if you can remember one thing from this IV curve of the SIS is that the pump characteristic of SIS has steps, and it's basically give us a diagnostic of how much halo we supply to the SIS, what is the halo frequency, and also tell us how good we can see the skyline using. That tells us how sensitive our device is. So of course, all this measurement need to be done below 5 Kelvin, way below the critical temperature of the superconducting material used for this SIS, niobium. So we've seen the mixer, we've seen the front end, and now I want to show quickly the local oscillator. So as I said earlier, the goal of the LO is to it's a frequency ruler basically. It has to be tunable, it has to be phase stable, and it has to be quiet. And usually we start from a 10 megahertz standard that we lock on a synthesizer, and we use multipliers to build up the frequency up to the interesting band. So we have a lot of multipliers in front of the initial source, and then we use PLL, the phase lock loop, in order to stabilize the signal. So the importance of LO is to be extremely pure and extremely stable. So we need locking mechanism and also filtering system in order to get a very pure and controlled single mode frequency, basically. So it's a lot of metrology and that comes from this generation. So mostly it's using Schottky mixers, Schottky diodes that allow this multiplication. And so going very fast, but we have seen local oscillator mixers, and we have seen the front end. And now I want to show you how we extract the intermediate frequency. And for that, we use PCBs, standard PCBs, but superconducting PCBs that allow us to have extremely low losses in the transmission of the signal, because so far we haven't got any amplification yet. So we just have the mixing, we extract the mixing with a wire bond to the PCB, superconducting PCB. And it carries also a bit more functionality. So for example, PCB is containing some impedance transformers. So the impedance of the SAS is generally not the same impedance as that you can carry on a SMA cable or K connectors. You need to have 50 ohms. So here we have a bit more impedance transformation. It also helps to bring the DC line. So we have a superconducting bias T attached to this PCB that allows us to bias the SAS without compromising the IF signal transmission. And also we provide on the same PCB this hybrid mixing, this 90-degree hybrid, the hybrid that allows us to recombine and split USB. So here we have the two mixers for one polarization, and here we have the output of USB and LSB. So that's right before we can finally amplify. So after these two outputs, we can use HEMTs. So the role of HEMTs is basically a two-port device, as you may know. It's basically provide a clean amplification between 10 to 30 dB on a broadband, so covering the full IF bands. So nowadays this low noise amplifiers are commercially available. You can buy them pretty much everywhere, and they operate at 4 Kelvin. And the state of the art now is the added noise of these amplifiers is quite low. It's only 2 to 4 Kelvin added noise. And now they can cover also very broad bandwidth, so up to 16 gigahertz instantaneous bandwidth. So there's a few suppliers in the world, and that's basically the result of more than 30 years of development on this technology, on this high electron mobility transistors. So it's radio astronomy started this business, and now it's used in quantum computing, and the field has come a long way to come to very low noise and extreme fractional bandwidths. And that's one of the main, I would say, hardware that we use in the back-end circuitry for radio astronomy. And finally, before I give some results of these receivers, I want to talk about the performances, and I want to introduce some I would say some terms that you might hear a lot in radio astronomy. So the receiver noise temperature, TR. It's basically the noise added by the receiver referred to the input. We have also you hear also the system noise temperature. It's basically what the receiver sees, what the sky sees. So it's going to be including atmosphere, receiver, and spillover losses. That's the system noise temperature. I will talk also I talked a bit before about IF bandwidth. So it's basically the usable passband after the mixing. So at ALMA, it's 4 to 8 gigahertz. At APEX, it's 4 to 12. And in the near future, it will be 4 to 20. I talked about image rejection, the sideband rejection. It's, again, I'll repeat, it's how well the wanted sideband is suppressed. So how clean USB and LSB are split. I will talk also about stability. So it's something that you would hear a lot also in radio astronomy. It's how long we can integrate a signal before we have 1/f drift dominate the noise. And of course, linearity and the compression points. It's that you hear in the LNAs. That you will hear that in the mixing. It's basically how much headroom you have before strong lines or continuum would basically flatten the response. How much power you would basically you won't see any changes in the response. So keep that in mind, because that's basically the performance chart that we will use, us as engineer and astronomers. That the terms that we use to estimate the capability of a receiver. So there's few techniques to allow us to estimate the performance of the receivers. The most common one is this hot and cold calibration method. So basically, we take the receiver with the horn antennas and the mixing element here, and we will show to this receiver two type of loads. One hot black body, which has a calibrated emissivity, and a cold the same black body but measured at cold. And usually we use liquid nitrogen for the cold loads and room temperature for the warm loads. And basically, if we have a very good receiver, the response should be linear. And basically, we use what's called the Y factor method. So record the output power or the output voltage of the receiver when it was shown a hot load and a cold load. We define the Y factor, and through a very simple linear algebra, you can basically extract the receiver noise temperature. So in operation, we also basically view the sky, and we also use a very simple atmosphere model to calibrate the opacity of the atmosphere in order to go from the receiver noise temperature to the system temperature. So the one note to be made here is that depending if you measure SSB, so single sideband, or DSB, when we quote the receiver noise temperature, we have different limits. So of course, with this, we have twice the amount of power received in one sideband, in the IF. So the quantum limit is not divided by 2. That's it. And of course, the thesis is also limited by the bandwidth of the instantaneous bandwidth of the receiver. And here is basically so that's the way we calibrate receiver. And basically here is the spec from ALMA. I take a spec of ALMA. So ALMA has an incident bandwidth of 4 to 8 GHz, and you see that basically all the receivers made for ALMA are contained between 4 quantum limits and 10 quantum limits. Okay, and in red, so that's the old, basically the old specification. You see that they were all aligned with more or less with 10K, 10 times the quantum noise limit. The upgrade that ALMA is planning for 2030, so will be more closer to 4 times quantum noise limit. So yeah, note that band 5 done by Chalmers. So we have already a 2 SB mixer with 4 to 12 GHz, not 4 to 8. And band 9 also was historically DSB, but we will have it has been upgraded to 2 SB in Sepia at Apex with a sideband rejection better than 20 dB. So if I compare that to Sepia, so that's my colleagues at Apex results. At Sepia, we have 4 to 12 instantaneous bandwidth and that's for the Sepia equivalent of band 7 of ALMA. We have a very good sideband rejection ratio and a very wide IF, and basically that's basically match what we will anticipate for the upgrade of ALMA. So one take-home result from that slide is that we need this lab calibration spec to estimate the probability of our receivers, but the true, I would say, the true result is when you do on-sky, when you take this receiver to the radio telescope and you do the on-sky baseline and you look at the stability. And that's the real exam for instrumentalists and radio astronomers. So as I promised before, I want to show some more or less recent results obtained with ALMA. And I arbitrarily picked 2, but there's plenty, of course. And if you open the astronomy astrophysics papers, you will find plenty of ALMA results. And the one that piqued my interest was this paper from Faccini using band 5 at ALMA, because it detected for the first time liquid water in in a protoplanet. So here we see ALMA images, so obtained with I think it was a very large baseline. We see the planet formation, so you see the disk of accretion around the star, and in blue, basically it's the water line that has been observed at 183 gigahertz, and I think that's quite striking because it's what's needed for life, for emergence of life, right? That's what we are talking about. It's one of the first observation of this water at warm water, not frozen, but warm liquid. Maybe that would basically allow emergence of life inside a telluric into a rocky planet in formation. So it's basically what you see here is it could be the emergence of a planet like Earth. So read the papers if you want to know more. And I think the most mediatic result of ALMA recently is this Event Horizon Telescope. So the EHT basically it's a millimeter VLBI telescope at 230 gigahertz, band 6. And it's basically used ALMA, phased ALMA into a single big dish that boosts the sensitivity of the EHT across a full array. And that made it possible to the observation of the M87 and Sagittarius A black holes. So you see in this image, if we didn't have ALMA, we would have not be able to resolve this bright disk surrounding the black hole. And so that's the initial results in 2019. Last year they did the same measurements, and they were also able to look at the magnetic the spiraling magnetic fields. They were able to observe the spiraling magnetic fields using, of course, the 2SB mixers from ALMA. So that's, I think, to me, one of the most flagrant use of ALMA in the recent years. So what's next for astronomers and instrumentalist people like me? So in the next few years, for 2030, we will have this wide sensitivity upgrade of ALMA. So now we will not 0 to 20, but 4 to 20. So astronomers want a wider IF with a faster digitizers and new correlators. So basically this, and that would help basically to triple the speed of the observation with ALMA. We'll be able to cover 2 to 3 times faster the spectral line service, and thanks to the new correlators. And of course, more bandwidth and more IF basically needs more. We need to have better data links, and WSU, so the sensitivity upgrade, also integrates faster data link. So right now, basically after the WSU, we will generate 1.2 terabytes of data per second per antenna. So it's extremely consequent amount of data that will come up from this WSU. And I think it's almost the end of my talk. And I want you to have a couple of takeaways with you. So in radio astronomy, the science case drive the RF engineering. So astronomers come to instrumentalists with requests. They want to observe certain lines. They want to have different dynamics. So that would basically tell us what kind of band we want to develop. If we need to have a 2SB setup, it would tell us the IF bandwidth, and it will also give us some idea of how good should we design for stability and for sensitivity. As you've seen, heterodyne receivers are a true RF engineering challenge. So we have a lot of discipline coming into it: superconductivity with the mixers, microwave engineering, and quasi-optics for the OMTs, the feed horns, the hybrids. We have a lot of needs for cryogenic engineering and mechanics. So you see everything has to be all tied together with very good mechanics. Local oscillators as well. That's also more like solid-state physics. And of course, IF and digitization. So mostly people developing analog to digital converters, also some low-noise amplifiers. So I would say the progress in this field is it's a mix of co-design and trade-off. So it's a trade-off between what the astronomers want and what the engineers can do. And usually the engineers can do a lot, but not everything what the astronomers want, unfortunately. And so we have to trade off between wideband optics, and quality of the signal, and what we can realize physically as well. Eventually, we reach limits of what we can manufacture. And I will stop here. And if you have any questions, thank you for your attention. Again, I condense in 45 minutes or 55 minutes, 8 weeks course, more or less. And what's coming up for me is, and my teams, is to the development of a new receiver that covers 2 bands at once. So we have some good results already, and a preliminary test at Apex coming in the next year. So thank you very much for your attention. And
okay, so thank you very much to Professor Joint for this very nice and beautiful presentation. So we have time for a few questions. So please raise your hand. We have something on the chat. The question, but so I have a question on my own. Currently, I mean, you just mentioned at the end that you need to comply with what astronomers want to measure, basically. So what are the current challenges for you, or in general, about the fabrication of the mixers or any devices that you're using?
I mean, so it's not just the mixers itself. I think it's if I go back, for example, to this image. So all this in this image, everything is done in Chalmers clean room. So the astronomers want larger bandwidths. They want and lower noise. So we use theory to develop and simulation to engineer this device, but eventually the bandwidths become so large that we have issues for example, impedance matching. So now the issues I face personally is integration. So we think we have enough good tools in the cleanroom to make so from lithography to sputtering to dicing techniques. So for example, something as easy as dicing that people can imagine actually becomes quite difficult for us because we need to be precise within few microns in dicing. The substrate thickness is very narrow. It's very 65 micron only. To manipulate that, it's a challenge. So after years and years of development, we are good at that now. But now the issue is the integration. How do you integrate this chip with the outside world? So we need to use PCBs and wire bonding. We need to use soldering, and all of those introduce losses, and that's the challenge. So I'm looking for people with ideas to tell me how we can integrate that cleanly, so I can remove all these interfaces. I don't want wire bond because those wire bond induce inductance, they induce losses. I don't want soldering because solder had losses, and we talk about very faint signal. So that's the challenge, integration.
Yes. Okay, good, thank you. So any more questions?
Of course, they can reach me by email, of course, for questions. If they need materials, I can provide material for the course as well.
Good to know. Okay, so if we don't have any more questions, we thank again Professor Joint, and we can go to the next speaker.
Thank you, Esteban.
Yeah. You can please just stop sharing. Yeah, thank you. Share. Sorry. So we would like to introduce now to Dr. Claude Leiner. I don't know if I pronounce that correctly. Who will talk about from concepts to systems in advancing photonic technology development. So, Dr. Claude.
Hello, everybody.
Hello.
So
We can hear you.
you can hear me?
Yes, yes.
Okay, fine.
Can hear you well.
So then let's start here. So can everybody see?
Yes, I can see it.
Okay, then I'm switching to the presentation mode. Can you see it in presentation mode now?
Not just yet.
Okay, then maybe I have to change something.
Maybe the button to the right corner.
So maybe now.
Now,
Can you see now?
yes.
Okay. So then. Sorry, I have a little problem that this is here. So now, okay. So thank you everybody to hear my talk. I want to talk a little bit from. I've chosen the title from concepts to systems, and I will talk a little bit about advanced photonic technology development and pioneer research materials. So. A quick overview about my presentation is first I would like to make a short introduction about uranium research and our institute materials here in Austria. Then I will present a little bit the technology chain at uranium research. We have from design to manufacturing and replication, everything in-house, and we're developing each steps of this value chain. So there's research done from the design to the origination to the replication. Then I will talk a little bit about the technology for advanced photonic system development, especially with a focus on the optical communication topic. Please excuse me a little bit. I'm not so focused on the optical communication. I'm doing optical design and freeform optic development. So I have taken much content of my colleagues and I'm presenting it here. So please don't be so shocked when I'm saying something a little bit wrong. And I will close up the discussion with real world examples from project we have made, also with a focus on optical communication. A little bit about our company. The Uranium Research is a research company with over 500 employees. We are something similar like the Fraunhofer in Germany, but here in Austria. And we are owned by the state of Styria. This is a department of the Austrian Republic. And other of these departments like Carinthia, Burgenland, and Vienna. And we are at 6 locations, and we have 7 different research units. And yeah, we have many different key numbers here. We have many publications, many R&D projects, and so on. And now I'm going to one of these 7 departments. This is the Material Institute. This is the Institute for Sensor, Photonics, and Manufacturing Technologies. And the institute has about 100 employees, and we have many different projects, even EU projects. We are splitted, or we have focus on 5 different research groups. This is the hybrid electronics and patterning, light and optical technologies. This is where I'm from. Then the sensors and functional printing, laser and plasma processing, and smart connected lighting. The director of our institute is Paul Hartmann. Here we are at 3 different locations. Even our institute is at 3 different locations. We have one location here in Weiz, where I'm sitting. Here we have 3 different research groups. Then we have one department at Niklasdorf and one at Pinkerfeld. This is at Burgenland. This is especially a smart connected lighting topic. And we are, or you can say we are one-stop shop for research projects. We are doing pilot line services for SMEs. We can upscale customers' lab samples and prototypes. We're supporting SMEs from TLA2 to TLA7. We are not doing production or something like that. We are only developing the production processes and transfer them to commercial companies. And we can also do customized material development, and we have a large laboratory infrastructure. Now a little bit about me. Like I said, I'm not directly from optical communication. I'm doing mainly, my main topic is the freeform micro-optics topic. So I will only talk 2 slides a little bit about that. This is, I think everybody knows, or everybody has something what freeform optics are. Freeform optics are optics where the optical surfaces is not defined by a mathematical function. For example, it is complete free. It is defined by the task the optics has to fulfill, and therefore you can make really tailored irradiance or radiant intensity distribution, and you have the highest degrees of freedoms in optical systems with them. One example which I personally like, one of the most, is the street lighting. This is when you have a street lighting, then you want to illuminate the street and not everything around, like windows, environment, nature, and so on. And when you're using here freeform optics, then you can save many light sources and many energy because you are redistributing the light emitted by the light sources only at the street. There are other examples like automotive heads-up displays and many other different fields. I will not say so much. Telescopes is one of the oldest fields, by the way. And what my main topic is not the freeform itself. This is a really big topic around the world. What we are doing here is we are making flat freeform micro-optics, because the problem about freeform optics is that it is hard to manufacture them. You have really sophisticated requirements on the material manufacturing side, and then your reproduction, it may be made injection molding, for example, but to make the molds, it is really complicated. And what we are doing is we are doing flat freeform micro-optics, and we can make it with laser structuring methods, and we can replicate it with ultra-cold nano-imprint lithography. But also it is possible to make it with injection molding. So this is only for my topic a little bit. This is part of the introduction. Now I will come to the technology chain at Euroneum Research. Here also, again, as an example, like I said, we have research topic around along the whole value chain. So we are doing this design. This is also my topic, where self-developed calculation algorithms are used to calculate these freeform micro-optics. Then we have a big optical simulation part where we can verify the optical functionalities of them. Then we have the origination. Here we have the laser structuring processes, which I will explain in much detail later. And then we have here, for example, the replication. This is here in this example with a roll-to-roll nanoimprinted lithography. We can also do it with step and repeat. We can do parallel laser structuring and so on. So we have the whole value chain along the manufacturing processes of optical devices. And here again, just a short example of the freeform micro-optics. Like I said, you only want to illuminate the street. Here is a 50 micrometer height structure. Here it is in the design. Here is already a scanning electron microscopy image of the structure. Here it is printed on a foil. Here you see the functional experiment. This is the LED on a wall. You see, this is the standard irradiance distribution. You have much light in the middle, and then it goes outside. And when you're using the freeform micro-optics, for example, then you have here a defined circle with homogeneous irradiance distribution and nothing outside of the irradiance distribution. That's just for my topic. We have done many different research fields already, many different structure types from plasmonic structures. We are doing even research in meta lenses now, cell substrate security features, microfluidics. Here are these freeform micro-optical elements. Then whiplets, for example, for big use on planes to save fuel and so on, and even decorative foils like sparkling foils. Now I come to the technologies we are researching and have in-house for the advanced photonic system development with the focus on optical communication. Like I said, the simulation is really a big part of optical device development, because it is an easy tool to have a clue what you want to do and what dimensions do you need for your optical device and how you can optimize it. And here, for example, we have ray tracing. This is a classical where you're tracing the rays to your optical system, and you can optimize, for example, here a structure for incoupling into such a waveguide plate for sensoring application, and you can optimize it for the rays to be mixed here, for example. These are structures for focusing, and here irradiance distribution to optimize, for example. So you can do a wide range for optical simulations with the ray tracing, but only where the wave nature of the light is not so important. More interesting, especially for integrated photonic circuits and integrated optics, is the finite difference time domain simulation method. This is solving the Maxwell equations by a leapfrog algorithm, and it is really numerical solving them in a time-dependent manner. So you can really make a simulation model of your integrated photonic circuits. Then you're starting with a plane wave or some other different light sources. You can define everything, and then you can say, okay, now propagate. Then the waves. Not the waves are propagating through your system, and it is really a correct simulation, like you're solving the Maxwell equations. So, like I said here, integrated photonic circuits you can simulate, Bragg couplers, everything here. Then here, these are waveguide splitters, for example, and here this is also Bragg coupler again. So this is really something you can make good simulations, what is happening in your devices to understand what is happening, and you can optimize your designs here. Another thing, this was my PhD thesis 10 years ago. What I did here is I combined both of these methods, because the problem is with the FDAD method, you can only solve small volumes, because it is really computer resource hungry, the simulation, and therefore it is only restricted to smaller volumes in the range of several tens of micrometers. And when you want to simulate optical devices which has diffractive optical elements and bigger refractive optical elements, like here, for example, you have two grating couplers on a wavegate plate, then you have to switch between these two methods to make a whole simulation of the device. And this is what I developed. I made some, I bridged between these two devices with self-developed algorithms. Here you can see this is a measurement of this this device where you have an input from the grate, where you incouple over the grating here and outcouple over the second grating, and this is here a wavelength. Here's the wavelength, and here's the diffraction angle. So here you see the measurement of the intensities, and here you can see the optical simulation results of the combined simulation. So as you can see here, this is in good accordance. So now I will go a little bit into detail about the laser structuring process we have here. These are especially interesting for manufacturing photonic devices for optical communication, for example. And let's start with one photon linear lithography. This is something pretty straightforward. Here you have a laser beam. It is focused. This is only a visualization of the laser beam, okay? Here. And then you see here is a focus. So you have here a certain focal width. And here you can use that for, you can use this focus for changing, for example, the material you are illuminating. When you have special photoresists, you can make a reaction in this photochemical. You can make a photochemical reaction in these resists so that they become, for example, soluble by a development step where you can remove the illuminated parts, and therefore you can make 2.5 dimensional polymer reliefs of structures like freeform micro-optics or different other optical structures. You can directly manufacture them with this technology. The next thing is when you're increasing, so this is here increasing the peak intensity of the laser. So this you can do in a continuous laser writing. This is already pulsed, and then you are compromising the intensity in these pulsed peaks, let's say. Here you can use the two photon lithography. This is already a non-linear process. Here you can see this is just a beam, and you can use it at every slice here as you want. And here you're using already a non-linear effect. This has some similar beam path like this here, but only the center here, so the smallest wing here inside, will interact with your material, because here you have so much intensity in this point here that two photons are absorbed at the same time. And this is a nonlinear absorption. And with two photons only at the same time absorption, you're making the photochemical reaction inside the resist volume. This means you can not only make 2.5D structures, you can make 3D structures, because here you can shift in the Z axis, in the X and the Y axis as you want. And now, this is, like I said, you can use that with special photoresists where you make a photochemical reaction. When you even further increase the peak intensity, then something different is happening. You are making damage to the material. So even a transparent material like glass or something, if you further increase it, you are damaging the material. And now, here again with the laser-induced material modification, you're using nonlinear absorption processes, but this is already multi-photon, not only 2, 3, 4, and so on, and avalanche processes in glass. And then you can make here localized and permanent structural changes in the volume of the glass. So you can change the reflective index, you can change the crystal structure, and so on. And this has, and with this you can make waveguide writing directly into dielectrics like glass or sapphire or something like that. And another application of this is the Fleiss process, but I will come later to this. If you further increase, and now you really have many intensity in your peaks, this is a really high values, this magnitude already higher, then you make laser ablation. And laser ablation is you are destroying the material entirely, you're whipping the electrons apart from the atoms, and everything evaporizes, it explodes. You can even use that to make material relief. So not only in polymer the structures, you can really make the structures directly into the material. But like I said, this is only an overview. I come to this later. So we have here different laser laboratories and platforms. One is the Optimal platform. This is a platform which is specialized on the first two processes, on the 1-photon lithography and the 2-photon lithography in the resins. So like I said, the 1-photon, you can make these 2.5D structures, and you are fast. You can see here, this is a structured area with a sawtooth structure here made of resins. You don't have to stay into these resins. You can make stamps out of them, and using nano and print lithography to reproduce them. So you're using that what you're making here. Then you're putting nickel or some metal onto it. Then you are removing the polymers. Then you have a metal stamp. And with the metal stamp, you can reproduce your structures in a nano and print lithography process. So these structures are reproducible with this process. Another thing is you can make 2-photon lithography. Like I said, you can really do 3D structures. Here's an example. You can even make, this is 10 microns only. You can even make a boat here made out of resist. This is interesting because it is often used to make optical interconnects. So when you have waveguides here, for example, in your material, or you have waveguide fibers even, this is even that made, you can process an optical system at the end of your fibers, for example. This is also made, and this can, and then you're staying with the polymer lenses, but they are really attached to your optical device. Another thing is it can even do a laser interference lithography. I didn't want to go into detail in this technique because of time reasons. There you have two laser beams which are interfering, and the interference where the laser is as the field is is increased here, then you have polymerization with that, and you can make big surface structures with this technique. Yeah, like I said, this is the Optimal platform. We have different research projects on this, even with self-learning algorithms, and we have monitoring and feedback control modules. So it is during the writing process, it is monitored, what is wrong and so on, and corrected, and you can even combine 1-photon and 2-photon lithography and so on. Next, I come to the frame-to-circumference laser micromachining. This is a platform which are using these higher intensity effects, like the modification of the material itself. So you have really high peak intensities here, and you can really structure your bulk materials with 3D geometries, 2D geometry, 2.5D geometries as you want. And you can make surface structuring, cutting, drilling of metals, semiconductors, ceramics, polymers, and transport substrates. And yeah, like the first one, it is maskless, and you can make a rapid prototyping process, and it has many different applications. Here, I'm going a little bit more into detail. Like I said, you have this non-linear absorption here only in the focal point, and here you have you're getting a certain peak intensity here in the material. Here you have this multiphoton absorption. So the electron here is the band gap, absorbs 1, 2, 3, 4, 5 photons at the same time, and now it is ionized. Then you have even of the avalanches functionality over time, which is even putting more intensity in the electrons, and therefore you get here hot electron ion plasma transfer energies to the lattice, and depending on the energy you can make different modifications of the bulk material itself. So at low pulse energies you can change the refractive index a little bit. There, with this you can make waveguides and even more complex optical structures like Mach-Bender interferometers, etc. When you're using higher intent energy, then you make really a change to the crystal structure. You have formations of nanogratings, for example, and the interesting thing is these nanogratings have different properties when it comes to wet chemical etch weights, for example. So they, when you're using chemical etching, the nanogratings are solved at a really higher weight than the normal bulk material. This is enabling a destructuring inside the materials with the Flies process. And at even higher pulse energies, like I said, you are evaporating these materials, and you can use laser ablation to make structures, surface structures, cutting or the drilling, for example. Now I come again to the lower energy processes. Here you see this is called the voxel region. This is the region where so much intensity is in the volume that 2 photon or the multi-photon processes are occurring. And here you can make a damage to the bark in a way that you can change the refractive index. This is when you make a densification of the structure, then you have a higher index. You can make a rarefication of the structure, so you're putting material outside, then you have some micro voids, and they are leading to a lower refractive index, or you have overlapping stress fields by doing 2 voxels at once, and you can create local regions where you're changing the refractive index. So this means you have different approaches to write waveguides. The most straightforward one is to make a single line waveguide writing. So you make here an increase of refractive index here where you're writing, and then you have here a waveguide, and the surrounding bulk material serves as your cladding, and then you can here make waveguides and couple light into it, and you can structure the waveguide arbitrarily inside the material. The next thing is you can make a depressed cladding waveguide. This is when you are using the second process where you make a rarefication. Then you are illuminating here the volume around the waveguide and making here some sort of cladding by the rarefication process. And the third one is, for example, the double line waveguide. This is where you're using the overlapping stress fields to create here in between these 2 beams a higher refractive index to make the waveguide here inside in between these double line illumination. Yeah, this is only for complication. You can primarily the intensity here is defined by the focal volume shape and the laser energy, but you can also make different parameters to make it better by, for example, the number of overscans. You can scan over the same area again and again to increase an effect. and you can use polarization, scan speed, pulse repetition rate to optimize your waveguides here. And like I said, this is a full 3D approach. That means you can really have your glass or sapphire or what else, and you can really write your waveguides inside it freely in a 3D process. Then when you have higher laser intensities, it becomes not only a densification or verification of the materials, it is really changing the crystal structure for this nanogratting formulation. And these structures show an enhanced etching sensitivity, for example, to HF or KOH. And this enables a 3D microstructuring inside the glass, for example, with the FLICE process. So this is FLICE stands for femtosecond laser-induced chemical etching. So this means in the first step you make a laser writing, so you're illuminating parts of your bulk materials you want to remove. There in these regions, the nanogratings are formed. And then in the second step, you make a selective etching process. These illuminated volumes are removed by the etching process because they have a higher etching sensitivity. And finally, you have a resulting 3D structure. Here you can see an scanned electron example from a microstructured bridge. This is a bridge. So this means here is nothing below this bridge. So this is really 3D, and it is in pore float glass. So this is all is glass. And this you can use for many different functionalities of integrated photonic devices. Here, and another example, for example, why this is really interesting, this is a microstructured hole, a drilled hole with this technique, but it is in sapphire wafer. And sapphire wafers are very, very difficult to pattern using usual techniques of the semiconductor industry. So this is really a technique where you can even micro-machining sapphire wafers or something like that. And the last thing is the laser ablation. When you even go higher with the laser pulse, then like I said, there are micro explosions in the material. So the laser beam is illuminating here, for example, a volume, and here's really an optical breakdown. So much intensity is put here that the electrons are ripped apart of the atoms, and it comes to a plasma expansion. So the electrons are flying away, the ions are flying away, and a shock wave occurs. But this is all in so short time periods that even when this region is so hot like a plasma, there's no time for the lattice of the material to transport the heat. So this means here's a plasma explosion of this material and nothing more. The rest stays the same. So this is really, you can really remove material here with this technique in a very, very precise way. And here you see examples from drilling from holes again. You can make it in different different materials. This is stainless steel. These are polymers, and even here you have it on printed photonic circuit boards. Here you can see here is an area where laser ablated. Here you can see different structures. Here is again closer, and here you see the resolution. This is really, really tiny. Just to sort what I said, we have a really big laboratory infrastructure. We have a light and integration laboratory with radiometric and photometric measurements. We have an electronics laboratory with design where we can design PCBs and so on, measure them. We have a surface characterization laboratory to see how our manufactured structures are compared to the design or to the ideal shape, for example, with atomic force microscopy, scanning electron microscopy, ellipsometry, and so on. And then we have a clean room certified with the ISO standard. And we have even a microassembly laboratory where we can make, like I said, these electronic designs into real components, SMD placing, soldering processes. And another thing which is really interesting for photonic devices is we have printed electronics and optics here. This means we have inkjet printers and so on for printing, for 3D contacting of electronic components. So in the last step, I will come to the real world examples. Here again, I will just show some things where we use the technologies I presented here in the third part of my presentation. So I want to start. This is something really interesting. This was the Smarted Surface. Smarted Surface was a project where this was only a part of it, where you have, for example, different surfaces, and you have, for example, buttons on the surface, like such devices, for example, and you want to backlit them, but you don't want to place the LEDs around the button all the time. And what we developed here is we have here the LEDs which are illuminating inside the waveguide. And what we did is we changed the direction of the light incoupled here by a surface structure. So this means here the light is incoupled and is bouncing back on top. And now it hits the structure and it's changing its direction towards this outer point. Then the next big thing, what we are doing in the smart connected lighting group, this is the visual light communication topic. This is visual light communication is when you have when you transport your data with light signals and using the already persistent light environment of buildings, for example. So this means you have your data and then you are modulating your LEDs to transmit, to change the electric signal into an optical signal, and then you can measure it with a photodiode and demodulating again to data. It is something like Wi-Fi, but with light, and it has some really big advantages to doing it with light. Not only from secure reasons, but you can use the existing lighting infrastructures, and you can combine it with visual light positioning and visual light sensing concepts. So this means you can not only transmit your data, you can see where you are, and you can measure your environment with this technique all at once. And there you have different, really much applications. Again, here is, for example, in traffic, here you can make a communication between two cars. By this light communication, you can measure, you can use the sensing principle to measure how much cars are driving here on the road and so on. You can use it in smart buildings and smart homes for the Internet of Things principle. You can use it in industry. This is really big topic. For example, for sensing communication of different assembling robots and so on. And you can use it even on logistics because you have the sensing positioning topic. You can see where is everything, where I want to guide my robots and so on. And for example, what we have done here is the visual light positioning topic. This is what I said I want to measure. I want to see, I'm now, for example, here, and I have my visual light positioning device, which can be my smartphone. And then I know, okay, I have communicated what is the locations of the different light sources here in my environment, like, for example, here, a train station or something like that. And now I want to know, but only I want to know where I am relative to everything. So only by the positions of the light sources, I'm want to determine with my smartphone where I am in the building. And this can be done with, here we have developed the optic, which is determining the position of you depending on the angles of incidence of the different light sources here. So this means you have different angles of incidence, then you get different focal points on the CMOS chip here. And another thing is, this is not an imaging optical system. You are seeing the focal points. So this means you are not making here pictures of the environment for security. You are not filming other persons or something like that. You only see the light sources here in such forms as you can see here. This is an animation where the position of the light sources change here. Theta like. You can see here, these are making some forms here on the CMOS chip. And when you know, and when you recognize these forms, you can say where are the light sources located around you, and you can make a triangulation or something like that. And together with the signal you have transferred, and you know where the light sources are, where the how are the rooms in the surrounding and so on, then you can say where you are. But only you know it, not the environment. There's no data going outside which can be processed by a third party. Another application of this is for what we have done in a project. This is geofencing. Geofencing is you have here, for example, a robot. Here is again our visual light positioning device onto it, and this robot here is traveling in a room, and we have said here in this red region, the robot is not allowed to go. So he is driving here around, he's driving here, and now he sees, I'm here at the border of the red line, but only he knows it. And then he says, okay, switching my green light to red. I have seen I'm entering that and I'm moving away. This is all automated process. Another application which is really interesting is fall detection for elderly people. Like I said, with a camera, which making pictures, everybody can do everything today with artificial intelligence. But I, from my side, I don't want to be filmed all the time, and I don't think everybody wants that. So again, here our principle, we have here 2 of our detectors on the shoulders. You can integrate it more than that. This is only a demonstrator. You can make this really in intelligent clothing and so on, and they are measuring where they are in the room. And now they can measuring it really so accurate, as you can see here, when you are seeing here, for example, 4 LEDs in the room, for example, at different positions, then you can make a 3-dimensional average positioning of 16 centimeters. So you can measuring, you're going from A to B, but you also can measure when you're making a fall. When you have a small and a fast change in the Z direction, then it is a fall. So you can say, okay, now I'm making an alarm that elderly people may be a fallen. Another thing was when we make the communication and using the sensing aspect of it. This is you are using the LEDs not only as emitters, as light emitters and signal emitters, but you can also use it as photodiodes. So you can change the functionality of the LEDs in a frequent manner that you're changing from illuminating to measuring. And this is what it makes so disruptive, because now you have, again, the persisting light infrastructure, for example, here in a tunnel, and you are switching the LEDs from illuminating to measuring. Then when a car is traveling below such luminaires, it makes such a profile. This profile, or called signature, is depending on their shape, color, and materials. And you can see here, this is a car, and this is a truck, for example. And here you can see different examples of this. This is a pickup truck. This has this signature. this is a larger truck, this is this signature, and this is a really large truck. So you can really distinguish these cars. And you can not only count these cars which are traveling, you can see which cars are traveling and so on with this technology. And this is also a real world example because this was an experiment made in a tunnel in Austria. So now I come again back to the waveguide topic. I will only go a little bit shorter toward this. This is, we are using this waveguide inscribing technologies for a quantum computer project. This is when you're making a quantum, everybody knows, I think, a quantum computer, you have qubits instead of bits, which can be entangled. And by this entanglement states, you can make more complex calculation processes at once. But there are different ways how you can realize a quantum computer. You need an object with quantum mechanical properties that you can make it to a qubit. One thing is to use trapped ions. And you're trapping these ions by using electromagnetic fields. So you're using lasers which are focused on these ions to trap them. And you use additional lasers to manipulate them. And the project OptoQuant was together with Infineon here in Austria to make such an ion trap and manipulation. And what you need for this is you have here, for example, your optical fibers. They are coming from your lasers. They are optically interconnected to your chip. Inside the chip, you have again a waveguide system. This is simple drawn, but it's way more complex than this. And this waveguide can be again inscribed by this femtosecond micromachining process. Then you have a beam out coupling. Here you have a focusing lens. You can make it either here, or you can integrate it even in the glass material. And here you have your ion trapped in the focus of these laser beams. And what we did here in the project is obvious. We made this glass light guide architecture. And this is not only one laser, this is more than one laser, because one laser is to trap them and other lasers are to manipulate them to get your information out of it to use it as a quantum computer. Another way to build a quantum computer is you can use photons as qubits. And also here you can use these 3D integrated waveguides. You can use here this waveguide writing again. Then you can make directional couplers. A directional coupler are two such waveguides which are written in parallel with a really low distance, and they act as beam splitters then. And you can make, additionally to these beam splitters, you can make thermal phase shifters here. And these thermal phase shifters are used to manipulate the optical system here from the quantum computer. And here you have all elements to make really a complex reconfigurable secrets for quantum state manipulation. So this means when you make it more complex, for example, here's just even an easy example, then you make here an architecture out of it to make weakly photonic devices with different points where you can make your heat manipulation. And what we did here, this is also we have written these waveguides, and then we have used the Fleiss process to make here these bridges, and these bridges serve as these thermal elements. So the advantage of using both processes in one platform is you don't have alignment problems. So we can write the waveguides with one laser, and then we are on the same stage, and we can write with the Fleiss process our other structures on it, and they are perfectly aligned. So, and the last example I want to show, this was really an older project, but this is the project which is most on topic, because here in this project, this was done more than 10 years ago. really done or really used here this waveguide widening course here still in resins to make a direct optical communication between a VCSEL cell and a photodiode. And here you can see here you have the VCSEL, then you have your micromirror, then you have here the written waveguide. Here you have again a micromirror which is focused on the waveguide again. Here you can see the transported cross section of the waveguide bundle. So this was really on point because this was really optical communication. So I want to thank you for your attention. And if you have questions, please feel free to ask.
Okay, we thank Dr. Leiner for this very nice presentation. And now it's time for questions, so raise your hand, please. No? We have a very quiet audience today. I have a question on my own about the holes that you perform with the femtosecond laser micromachining. How deep you can go? Can you go through silicon bias, maybe?
Somewhat.
Yeah.
How deep in
For example, silicon wafer.
centimeters or?
Can you go through a silicon wafer, for example? Yeah.
Yeah, I think yes.
Yeah. Right.
Like I said, it is not my topic. This is of my colleague here, but I think you can really do it on a wafer scale level. So this is, and
Okay.
you're going deep here also. So this is you only need the right wavelength of your laser. This is always the key, because when you're doing silicon, for example, then you need a laser which is transparent for the silicon, and then you make in the focal you make the 2-photon absorption, and then you have these processes.
All right.
But like I said, the lab here, the femtosecond lasers micromachining lab has 5 different lasers at different wavelengths. So to have this broad materials range, you can micromachine.
But this is I don't know if you're into the details, but when you do it, you're modifying the materials, so later you can remove it by some wet chemical, right? Or is it directly done on the sapphire in this case?
Yeah. There are 2 different laser processes. One you're doing with the resins, and one you are doing with the materials directly. The micromachining is when you're doing it with the materials directly. So here you only have the sapphire, for example.
All right.
Okay, and you're illuminating the sapphire here that you're illuminating the hole, and with an energy that it makes this nanograting formation here inside the hole. And then you are putting here it in the etching bath, and the hole is etched by this process, because here inside is the nanograting, and the nanograting is really enhanced for the etching process. So the etching is really fast here in the hole, but not fast on the outside. So this is how you make these holes. Yes. But you don't have another material than sapphire in this process now.
I understand. Okay, thank you very much. Berma, there's a question, I think.
Hi, so I have a question regarding etching of the material with the laser. So can we use this technique for etching the quartz crystal? Are we using it?
Yes, of course. The example number 1 was borofloat.
Okay.
So you can use it really on different materials, yes. And the advantage is that you have the structures in this material. So you have a monolithic material with structures. This is for many applications. This is really important.
Okay, so I mean, can we do it for a higher aspect ratio, like more than 50 micrometer, and with like 2 micrometer of diameter or something?
I think yes. I think even yes. But for exact values, you have to talk with my colleagues.
Okay, I was curious because high aspect
but
ratio quartz crystal is quite difficult. Yeah. Okay.
yeah, because now two things. Okay, in principle, illuminating, you can illuminate in 3D in the object. Okay, because you have only the writing the writing voxel. This is only a point, and this focus point can be changed inside the material as you want. And then you are illuminating your material and make this nanograding formation in every region you have illuminated, and then you're going to the etching path. And the etching is normally etching everything, but really magnitudes higher the surface you have illuminated before.
Okay.
And so I think it is possible to make even high aspect ratios, yes. But like I said, I'm not an expert in this topic.
Okay. Yeah, thank you.
You're welcome.
More questions? Got 5 minutes. Maybe one more question. Okay, so yeah, we have arrived to the end of this digital school. So I would like to thank you again to the speakers for their kind collaboration, and everyone else, to all the attendees for coming today. I think they have been pretty nice presentations, very interesting, all of them. So I just want to remind you that these webinars will be soon posted in the YouTube channel of INFRACHIP. So you can go and watch it again and maybe contact with the speakers for future collaborations. Don't forget to subscribe to the newsletter, INFRACHIP newsletter, and follow us on LinkedIn. And stay tuned. So again, thank you very much, and I hope you have a nice rest of the day. Bye-bye.
Thank you. Bye-bye.
Bye.
Bye.